Hand and power tools are the hands and muscles of a carpenter's workshop. Classification: 1. Measuring and layout tools, tape measures, combination squares, marking gauges and levels. They tell you where to cut, drill, or place a fastener, much like a GPS tells a driver where to turn. 2. Cutting tools, handsaws, backsaws, chisels, planes, and power saws, such as circular, table, miter, and band saws. Think of a handsaw as a pair of scissors for wood. A circular saw is a fast-moving kitchen blender that slices through large boards. 3. Shaping and refining tools, files, rasps, sandpaper, hand routers, power sanders. They smooth rough edges the way a painter brushes a canvas. 4. Joining and fastening tools, hammers, mallets, screwdrivers, nail guns, power drills, impact drivers, biscuit joiners. A hammer is a simple lever that converts a swing into a sharp impact. A nail gun does the same with compressed air or electricity, delivering many hits per minute. 5. Holding and fixturing tools, clamps, vices, bench dogs, workbenches. They act like a pair of strong hands that keep the workpiece still while you work on it. Function: measuring tools set the blueprint on the wood. Cutting tools remove material to obtain the shape. Shaping tools refine the cut to accurate dimensions and smooth surfaces. Joining tools create the connections that hold pieces together. Holding tools maintain position and safety during all steps. Each tool type has a hand-operated version, low power high control, and a powered version, high speed less fatigue. The carpenter chooses based on the size of the job, required precision, and time constraints, just as a driver picks a bike for a short city ride and a car for a long highway trip. Choosing the right tool, keeping it in good shape, and working safely are 3 pillars of any woodworking shop. Tool selection: fit the job. For a delicate dovetail, a fine-toothed backsaw and a dovetail marker give control. For a 2x4 frame, a 7¼ circular saw and a framing nailer speed things up. Material compatibility: use carbide-tipped bits for hardwoods. High-speed steel HSS works fine on soft pine. Ergonomics: a lightweight screwdriver reduces arm fatigue. A well-balanced hammer reduces rebound. Maintenance: cleaning: after each use, wipe away dust and resin. A dusty blade can overheat and lose sharpness. Sharpening: planes, chisels, and saws need a keen edge. For a hand plane, set the bevel angle usually 30 degrees and use a sharpening stone or a jigged grinder. Power saw blades are sharpened with a carbide file or replaced when teeth are worn. Lubrication: moving parts such as drill chuck and nail gun driver need a few drops of light oil to prevent seizure. Inspection: look for cracked handles, frayed cords, or broken safety guards before each shift. Safety procedures: personal protective equipment, PPE, safety glasses shield eyes from chips. Hearing protection stops ear damage from loud saws. Dust masks or respirators prevent inhaling fine wood dust. And sturdy gloves protect hands, but avoid gloves when using circular saws because they can be caught. Machine guarding: never remove blade guards, anti-kickback pawls, or magnetic switch-off devices. Work area: keep the floor clean, secure cords, and ensure good lighting. A cluttered floor is a tripping hazard, just like a messy kitchen leads to spills. Procedural safety: always check that the workpiece is clamped before cutting, keep fingers away from the cutting zone, use a push stick for small pieces. Emergency readiness: have a first aid kit, fire extinguisher class A for wood, and know the location of shutoff switches. By matching the tool to the task, keeping it sharp and clean, and always observing safety habits, a woodworker reduces waste, improves quality, and stays injury-free. Wood joints are the bones that hold a wooden skeleton together. The most common joint families are 1- butt joint - 2 pieces meet end to side or side to side with no special shaping. It's like stacking bricks flat, strong only when reinforced with screws, nails, or adhesives. 2- lap joint - each piece is cut back a lap so they overlap, sharing material. A half lap removes half the thickness, giving a flush surface. Think of 2 overlapping book spines. The overlap gives more contact area. 3- dovetail joint - interlocking pins and tails that resist pulling apart. The shape is like a key and lock. The wider tail blocks the pin from sliding out, making it ideal for drawer boxes. 4- mortise and tenon - a rectangular tongue tenon fits into a matching cavity mortise. Like a wooden Lego brick, the tenon bears compression, the mortise resists tension. 5-rabbit joint - a step cut along the edge of one board that receives the face of another board, similar to a picture frame groove. 6-dado or groove joint - a slot cut across the grain that a board slides into. It's the wooden equivalent of a shelf slot. 7-biscuit joint - a small oval wood biscuit inserted into matching slots and glued. The biscuit swells with glue tightening the joint. 8-pocket hole joint - a drilled angled hole that accepts a self-tapping screw, quick for cabinet frames. Structural characteristics. Contact area - more surface area equals higher shear capacity. A half-lap joint has double the area of a simple butt joint. Mechanical interlock - dovetail and mortise and tenon create geometric resistance to pull out, similar to how a puzzle piece stays together. Grain direction - aligning grain across the joint, for example in a mortise, improves strength because wood fibers carry load better along the grain. Stress distribution - joints that spread load lap dovetail reduce stress concentration, much like spreading a weight across a wider base. Ease of construction - butt joints are fastest. Dovetails require skill but give the strongest, most decorative result. Understanding each joint's geometry helps the carpenter choose the right one for load type, shear, tension, bending, and aesthetic preferences. Explanation - designing a joint is a bit like drawing a map before you build a bridge. Geometry tells you where to cut, how much wood to remove, and what angles will give the strongest fit. 90 degrees right angle - most common, a square corner. Use a combination square to verify. 45 degrees miter - two pieces meet on the edge to form a right angle. The miter saw is set to 45 degrees. The math is simple. Each piece is cut at 45 degrees, so the sum equals 90 degrees. 30 degrees / 60 degrees complex miter - used in hexagonal frames. If a piece is cut at 30 degrees, the complementary piece must be cut at 60 degrees. 30 degrees plus 60 degrees equals 90 degrees to meet flush. A dovetail tail width W and angle theta define the pin width PP equals W minus 2 times L times tangent theta, where L is the length of the dovetail tail. Example, tail width equals 12 millimeters, angle equals 8 degrees, tail length equals 30 millimeters. Tangent 8 degrees approximately 0.1405. P equals 12 minus 2 times 30 times 0.1405 equals 12 minus 2 times 4.215 approximately 12 minus 8.43 equals 3.57 millimeters. So each pin will be roughly 3.6 millimeters wide. Tenon width TW is usually 1/3 of the parent board thickness T for strength. TW equals T divided by 3. Mortise depth MD should be 2 to 3 times tenon width to give enough bearing surface. MD equals 2.5 times TW average choice. If a 45 mm thick timber is used, TW equals 45 divided by 3 equals 15 millimeters. MD equals 2.5 times 15 equals 37.5 millimeters. A layout square provides a 45-degree line when its sides are equal. For a half lap, the depth of each cut is half the board thickness. If a board is 20 millimeters thick, each lap cut removes 10 millimeters, leaving a flush surface. Coordinate system, place the origin at the inside corner of the joint. Plot each cut line using x, y coordinates. Example, for a 90-degree lap, cut line A runs from 0, 0 to 20, 0 horizontal, line B from 0, 0 to 0, 20 vertical. By combining simple angle rules, trigonometric formulas, and proportion tables, the carpenter can predict exactly where each cut belongs, avoid waste, and ensure a tight fit. Quick checklist. 1. Identify joint type, arrow find governing geometry. 2. Write down known dimensions, board thickness, width. 3. Apply proportion rules, for example tenon equals 1/3 thickness. 4. Use trigonometry if angles are involved, dovetail, angled braces. 5. Sketch or plot the layout before cutting. Explanation: a joint's ability to carry load depends on how the forces travel through the wood and where the weakest points lie. 1. Load types. Shear forces slide one part past another, for example a shelf supporting books. The joint's bearing area resists shear. Tension forces pull the joint apart, for example a drawer pulled open. Mechanical interlock and glue prevent separation. Compression forces push parts together, for example a post bearing weight. Wood fibers in compression are strong if grain runs continuously. Bending or moment forces cause rotation about a point, for example a cantilevered beam. The joint must transfer bending stress to the adjoining member. 2. Stress distribution. Stress sigma on a joint is calculated as sigma equals F divided by A, where F is the applied force and A is the effective area resisting the force. Butt joint is just the nail or screw cross-section, leading to high sigma, which is weak. Half-lap joint is approximately 2 times board thickness times width, so sigma is halved, making it stronger. Dovetail A includes the interlocking area. Geometry redirects tension into shear on the tails, dramatically lowering sigma. 3. Failure modes. Butt joint typical failure is pull out of fastener or wood split, because the bearing area is small and the wood grain may split under tension. Lap joint typical failure is shear crushing of wood at the overlap, due to high compressive stress where the two pieces press together. Dovetail joint typical failure is cracking of tails if grain not aligned, because the tails experience tension and grain crossing the tail weakens it. Mortise and tenon joint typical failure is tenon shear or mortise wall crushing, caused by excessive load without glue or a tenon that is too thin. Pocket hole joint typical failure is screw pull-out or wood splitting, due to short screw length and poor grain direction. 4. Design for strength. Increase bearing area, use longer tenons, deeper mortises, or larger lap overlap. Grain orientation, align grain parallel to tensile forces. Avoid grain crossing the joint's load path. Mechanical interlock, dovetails, tenons, or biscuits provide geometric resistance. Adhesive use, proper glue spreads load across the entire joint surface, reducing point stresses. Fastener selection, choose screw diameter and length to give enough shear area. For example, a number 8 screw has a root area approximately 0.5 square millimeters. Multiple screws share load. 5. Example calculation, shear capacity of a half-lap joint. Assume board thickness T equals 20 millimeters, width W equals 100 millimeters, overlap depth equals 10 millimeters, which is a half lap. Allowable shear stress for pine tau allow equals 4 megapascals. Effective shear area, A, equals 2 times T divided by 2 times W, which simplifies to T times W, equal to 20 millimeters times 100 millimeters, that is 2,000 square millimeters. Maximum shear force, F max, equals tau allow times A, 4 newtons per square millimeter times 2,000 square millimeters, which equals 8,000 newtons, approximately 0.8 kilonewtons. So the joint can safely carry about 80 kilograms of vertical load before shear failure. Understanding how forces travel and where stress concentrates lets the carpenter size joints correctly, choose the right fasteners, and avoid unexpected breakage. Carpentry work is not just craft, it is also governed by industry standards that ensure safety, interchangeability, and quality. 1. Tool standards. ANSI/ASME B107.1 Safety requirements for hand tools, e.g. handle strength non-slip grips. ISO 12100 General Principles for Machinery Safety applies to power saws, routers, nail guns. UL/CE markings electrical equipment must meet Underwriters Laboratories US or CE Europe certification for voltage grounding and fire resistance. EBL European blade length defines maximum blade size for table saws to keep guards effective. 2. Joint specification standards. ANSI A108 standards for wood joinery covering dimensions for mortise and tenon dovetail, and lap joints used in furniture and building construction. ASTM D2555 test method for shear strength of wood adhesives important when specifying glue-bonded joints. ISO 10045 requirements for mechanical fasteners, screws, nails used in timber structures. Building codes, e.g. International Residential Code, IRC National Building Code of Canada NBCC, provide minimum requirements for load-bearing joints in framing, e.g. required nail size and spacing for floor joists. 3. Dimensional tolerances. Nominal versus actual size. A 2x4 is actually 1.5 inches by 3.5 inches. Standards define these nominal sizes, so designers can specify material without confusion. Tolerance zones for mortise width. ISO 1105 may allow ± 0.1 millimeters deviation to ensure a snug but not overly tight fit. 4. Documentation and certification. Material Test reports MTR provides species-grade moisture content and strength class of lumber, e.g. SPF number 2, 1,500 pounds per square inch. Tool calibration certificates, laser levels, and digital angle gauges must be calibrated annually according to ISO/IEC 17025. 5. Why standards matter. Safety. Properly rated nail guns prevent accidental discharge. Interchangeability. A 1-inch drill bit will fit any standard chuck. You can buy replacements from any supplier. Legal compliance. Building inspectors will reject a deck that does not meet IRC nailing schedules. Quality assurance. Consistent joint dimensions lead to tighter fits and longer-lasting furniture. Carpenters should keep a copy of relevant standards on the job site. Verify that tools carry the proper certification marks and select lumber and fasteners that meet the specified grades. This reduces rework, improves safety, and ensures the finished product meets professional expectations. A quick reference sheet. Hand tools ANSI/ASME B10 7.1 handle strength ergonomic grips. Power tools ISO 12100 machine guarding emergency stop. Lumber grading ASTM D245 strength class knots moisture. Wood joints ANSI A 108 dimensional rules for mortise tenon dovetail. Fasteners ISO 10045 thread dimensions shear capacity. Building code IRC Chapter 6 nailing schedules for joist studs. By aligning everyday practice with these standards, carpenters turn art into reliable engineering. 6. Maintaining compliance. Keep tools inspected yearly. Store certification documents with project files. Use a checklist before each build to verify that all materials meet the required standards. Problem 1. Tool selection and safety. A carpenter must cut 12 2x4 studs to a length of 2.4 meters for a platform. The job shop has only a 7 1/4 inch circular saw, a hand-held miter saw, and a table saw. Which tool should be chosen to maximize safety and efficiency, and what personal protective equipment is required? Solution 1. Tool choice. The circular saw is portable and can cut long lengths, but it requires a guide and is less accurate. The table saw provides a fence for straight cuts, but the material length exceeds the table's capacity. The miter saw can only cut up to 1 meter. Therefore, the circular saw with a straight edge guide is the best choice. 2. Safety gear. Safety glasses, hearing protection, dust mask, and sturdy work boots. A push stick or guide clamped to the workpiece keeps hands away from the blade. 3. Procedure. Clamp the stud, align the guide, cut with the saw at full speed. Let the blade reach full revolutions per minute before feeding. Problem 2. Joint geometry. A half-lap joint will be made from 2 30mm thick boards. The design calls for each board to be notched to half its thickness. What is the depth of each notch, and what is the total material removed from each board? Solution. Half thickness equals 30 millimeters divided by 2 equals 15 millimeters. Notch depth equals 15 millimeters. The board is cut 15 millimeters deep. Assuming the notch runs the full width of the board, say 100 millimeters, material removed from one board equals depth times width equals 15 millimeters times 100 millimeters equals 1,500 square millimeters. 2 boards total removed equals 3,000 square millimeters. Problem 3. Dovetail calculation. A drawer front uses a dovetail where the tail width W is 12 millimeters, the tail length L is 35 millimeters, and the dovetail angle theta is 8 degrees. Calculate the pin width P. Solution. Using the formula P equals W minus 2 times L times tangent theta. Tangent 8 degrees is approximately 0.1405. L times tangent theta equals 35 millimeters times 0.1405, approximately 4.92 millimeters. 2 times that equals 9.84 millimeters. P equals 12 millimeters minus 9.84 millimeters, approximately 2.16 millimeters. Thus, each pin will be roughly 2.2 millimeters wide. Problem 4. Shear capacity of a mortise and tenon. Select a tenon for a 45 millimeter thick beam. The allowable shear stress for the wood species is 5 megapascals. The tenon will be 15 millimeters wide and extend 40 millimeters deep into the mortise. Determine the maximum shear force the joint can resist. Solution. Effective shear area. A equals width times depth equals 15 millimeters times 40 millimeters equals 600 square millimeters. Maximum shear force F max equals allowable shear stress times A equals 5 newtons per square millimeter times 600 square millimeters equals 3000 newtons, approximately 0.3 kilonewtons or about 30 kilograms. Problem 5. Fastener spacing per building code. The International Residential Code requires floor joists to be nailed with 16 penny nails spaced not more than 7 inches on center along the joist. If a joist is 12 feet long, how many nails are needed on each side? Solution: convert length to inches. 12 feet times 12 inches per foot equals 144 inches. Maximum spacing is 7 inches, so number of spaces equals 144 inches divided by 7 inches, approximately 20.57, round up to 21 spaces. Number of nails equals spaces plus 1 nail at each end equals 22 nails per side. 2 sides gives 44 nails total per joist. Problem 6. Tool maintenance. A planer's cutter head is dull and produces a surface roughness of 12 micrometers. The specification calls for less than or equal to 6 micrometers. If each sharpening restores the edge to 3 micrometers roughness and each use adds 0.5 micrometers, how many cuts can be made before the next sharpening? Solution: starting roughness after sharpening is 3 micrometers. Allowed increase equals 6 micrometers minus 3 micrometers, 3 micrometers. Each cut adds 0.5 micrometers, so cuts before exceeding the limit equals 3 micrometers divided by 0.5 micrometers per cut, 6 cuts. Problem 7. Standard compliance check. You are ordering 2x4 lumber for a deck. The local code, International Residential Code, requires lumber classified as number 2 Southern Pine, grade SBF, minimum 1,500 pounds per square inch bending strength. The supplier offers SBF number 3 at 1,300 pounds per square inch. Is the material acceptable? Explain. Solution: required grade is number 2, higher than number 3, and minimum bending strength 1,500 pounds per square inch. Supplier material is number 3 and only 1,300 pounds per square inch, both below the code. Result: not acceptable. The carpenter must request SBF number 2 or higher that meets the 1,500 SI requirement.